Campinas, Professor Guido Araujo, to share his talk with us today. Professor Araujo research involves code optimization, parallel programming, computer architecture, hardware acceleration, often in close collaboration with important companies. And his work has been extensively distinguished with awards such as Best Paper, Best Thesis, and other academic recognitions. And today he's talking with us about coding optimization to hardware AI. And I believe with our efforts to bring RISC-V to hardware AI, this topic couldn't be more timely. So thank you, Guido.
It's working. Okay, folks, I'm an university professor, then please control my time, okay? Because, you know, university professors tend to go forever talking, right? So, yeah. All right, so I would like to give with this talk a perspective, what happens in interface between compiler and hardware AI, okay? It's a kind of hard topic in general because you have so many hardware architectures out there, and be able to design a compiler toolchain which could be kind of code-to-code easily retarget to the different targets is a very challenging endeavor, actually. But okay, let me see if I can give you folks kind of a glimpse on that. One of the most important optimization that an AI compiler can do is tensor slicing, right? AI is a very boring problem. If you look at the perspective of compiling technology, very boring because at the end of the day is a problem of optimizing data movement. And data movement comes from memory, memory is slow, and you have to optimize that. Computation for AI is again boring in the sense that if you do the standard generic matrix multiplication efficiently, or being outer product or inner product, you're going to do a very good job. But so at the end of the day, think that compiling for optimization under a compiler technology for AI is a data movement problem. So you have to move data around, right? Data is huge, and at the end of the day, you have to slice the data to being able to accommodate that inside the memory, on die memory. That's the biggest issue that you need to handle on a relevant optimized compiler for AI hardware. All right, so this thing doesn't work as a pointer, and I'm going to use my finger because, I mean, you know, most of my career is doing classes, right, and teaching. All right, so we're going to talk a little bit about the work we did for slicing x86 and Power 10 mix multiply assist hardware. Is doing slicing for RISC-V neuromorphic processor from LG Electronics. And I will end with just a few words of the current work that we are doing using MLIR transform dialect, which was proposed by folks like Alex Zinenko, that was in Google, not anymore. We have used this transform dialect to have a more generic toolchain, compiler toolchain for AI hardware. All right, so let's move forward. So let's pick the classical example. Okay, we're talking about a CNN model, very classic stuff. Most of the computation happened on these yellow blocks here. Around 70, 80, sometimes 90% of the computation is there. All right, so you want to optimize most of the computation. Of course, you're going to focus on those. And as most of you know, the tensor sizes for the inputs and for the filter differ according to the convolution layer you're talking about. In the very beginning, the input layers, the input tensors for the early layers is huge, and the weight tensor is small, and this thing gets changed as you go. So you want to have an optimizing compiler which takes this into consideration. If you have a huge input tensor, a small weight tensor, in the beginning, you want to focus your attention on the input tensor because you don't want to move data around. So you want to take a small slice of the input tensor, move it through the cache hierarchy. We are talking about the CPU classic cache hierarchy, L3, L2, L1, and move it up in the hierarchy and just touch that slice once and never touch it again because the input tensor is going to be huge. But as you move through the other convolution layers, the weight tensors become big and the input tensor is small. So we want to do the other way around. You want to slice the weight tensors and touch one of the slides for the weight just once because it's huge, okay? So that's a very important, relevant issue if we're gonna do slicing for AI approach. So what is the problem? You have the filters or weights, you have this input tensor here, it's larger, and what you want to do is to slice this guy and touch them once, it goes up the hierarchy, stays there, and never more touch that slice anymore, right? It's pretty much standard stuff. So you want to slice this guy because it's larger, do the convolution, and produce an output block. Okay, so let's go over a bit of the work we did for x86 and Power 10. We designed this convolution compiling flow here. Just going over it quite quickly. What we do is a classical convolution slice analysis here. We take into consideration the cache size for that. So we take into consideration the sizes of the cache very early on in the compiler flow. We don't do that down there because it's really important to bring architectural information up the hierarchy. And the convolution slice analysis produces a tiling strategy. It says how you're going to tile the input and the weights, right? The tiling strategy is fed what we call the convolution slice optimization. So optimization has a number of tasks here, these 3 tasks. Generate the loop nest, it's a 6-level loop nest. Generate the input packing, how you're gonna pack the input. I won't go much into the detail, but people underestimate the amount of computation time that you do doing packing. Sometimes it takes like 20 to 25% of computation time. So don't underestimate packing, okay? Packs are very relevant optimization. And then do the microkernel. And this microkernel is something that you can recycle from BLAS, for example. I'm not going to talk about the package filtering, because you can do this in compile time. It's, again, very boring. And after that, you just lower this thing to the regular LLVM-IR approach. All right, so let's first talk about convolution slice optimization. If you guys know well the compilation flow for BLAS, for GEM, classical GEM, you know this paper by Guido a long time ago that says that, okay, you have the 6-level thing with lots of tiling, and you basically are going to have a microkernel here, which is going to repeat the convolution operation there. But the go-to paper was targeted to GEM, the generic matrix multiplication. What we did in this work was basically kind of do the go-to approach to convolution. Okay. All right, so if you can look, I don't want to go deeper in this detail, of course, you can look at the paper, but what we have is a 6-level loop nesting, and you have lots of code here which just generate the microkernel, and then inner here you're gonna have the macrokernel, and inner here the microkernel. This guy, the neat thing about this approach that if you want, you can take your BLAS microkernel and recycle it for this. You don't need to redesign it. And this is very relevant because if you have a very strange architecture and you design your own microkernel by hand, you write it in assembly or intrinsics, you basically can recycle it, have it working for BLAS and recycle it into this approach. You don't need to do the redesign it. The neat thing about this is that your programmers, which know pretty much your target architecture, can hide all the microarchitecture details inside this microkernel, okay? So pretty much the approach from the layer 5 down to the microkernel call is machine independent for this specific cache hierarchy-based target. All right, so we talked about the loop nesting generation. That's something that compiler slice optimization do. Let's talk about the microkernel. As I said before, we are using an outer product microkernel. Can be the same use for matrix multiplication. You can recycle it from BLAS. This seems to be like just a detail, but it's not. Assume that you design this very weird architecture which does very efficiently matrix multiplication. And you have it in BLAS, so your applications can already use that, right? So BLAS is using lots of machine learning tool chains. You can just take that guy, okay, and move it into your compiler framework without any further work. All right, so let's look to the some other tasks that the CSO optimization needs to do. All right, a very important one is do the slicing, okay? You can pick whatever strategy for a slice you want. If you have lots of time to spend, you can just take TVM and spend like hours through some genetic algorithms the best styling. That's nice. It's going to work for regular x86-based architecture. It's going to work for GPUs. But if you have this strange architecture, it's going to be really hard for TVM to find the proper optimization for you, or proper slicing, okay? Let me just give a short overview how this thing works. It's very classical. Some folks will know this pretty well, others don't, but I want to make it clear. Remember that I mentioned about the input, the filters, and the output, right? So the filters are, the inputs are these little green blocks here. The weights are these little blue blocks, and the output is the red block. And you have the classical cache hierarchy. So I'm assuming that my inputs are huge. So you want to slice the input, get one very little green block here, the input, and touch it just once. Because you have many of these green blocks, and you don't want to retouch it again, right? So you focus, in this case, in keeping the green block stationary into the L1 cache. All right, so how would this work? So you touch one, it's in memory, you bring it to L3. Naturally, you don't have control of that because it's automatic. And you bring the weight there as well, right? And this thing moves up in the hierarchy. It goes to L2, of course, it goes to L1, and that's it. When it reaches L1, you're going to do the weights convoluted with the input, and then get an output, and eventually you can store that down. Okay, so you want to keep the little green block here stationary in the cache, because you're going to reuse it to do convolution with the other blue blocks, which are the weights. That's really important because you don't want to touch this green block more than once, because if you pollute the cache and you have to go back to memory and bring it up again. And you don't want to do that because, remember, you have many green blocks because the input tensors are larger. We're talking about convolution very early on in the CNN model. All right, so it's already in the cache, and then you touch another weight. You're going to go over the weights, the blue cubes, and do the convolution with that guy there. So it keeps going up the hierarchy as you touch it. Go up again, you produce another output. Okay? So keep doing that. You touch another blue cube, correspond to another weight. See, the green block is stationary in cache, right? It keeps going up and up. Of course, this is natural. It just happens, right? The compiler doesn't have control on this because you're talking about classical cache hierarchy. And you do another convolution, get another red block, which is the output. And then you finish up with that green block. You're never going to touch it again, right? So you touch the next slice of the input. It goes up the hierarchy, and then repeat everything again. You go and convolute it with a weight, but please notice, if you do the proper analysis, the blue slice for the weight is going to be in L2. It's not going to be in memory, okay? So we can touch it again. It goes up the hierarchy, not from memory and through L3, but just from L2 to L1. Do another convolution, and you keep repeating that for the second input slice, right? Keep rotating the weights there, preferably using those that are L2 already, and you keep doing that. And it keeps going, and then assuming that you just have a tensor with 3 slices, like these 3 blocks, you basically didn't touch memory again, right? Of course, it's not the common case, but somehow you reuse the weights which are in L2, okay? And when you finish that, you're never going to touch this blue slice again. Okay, sorry, green slice again. All right. So there are a bunch of equations associated to this. Mostly what you have to assure is that the size of the input tile, this green guy, size of the weight tile, this blue cube here, L1, and the size of the output tile, they're smaller than the size of L1 with a little margin, right? Because you don't want, I mean, somehow things get polluted, and you want to have just this little margin. So we have this equation which constrains L1, a similar equation which constrains the L2, and a similar equation which constrains the L3. So your optimization problem is, I want to find K1 and K2 such that you satisfy this, okay? So your tiny algorithm will basically find K1 and K2 for that. There are many ways to do that. You can just be aggressive and throw this into an LLP problem and wait forever to get the proper slicing. Yeah. Proper slice means, what is this, the quantity for K1 and K2. I mean, but an LLP is kind of overkill for that, okay? What we basically did was a very, very straightforward binary search algorithm to find the size of K1 and K2, okay? And you can use this binary search algorithm with some adaptations hierarchically, which produce good results. All right. So remember, this is just one of the tasks that the compiler has to do, the tiling, the proper tiling, okay? Let's now go over how the real convolution happens, right? Most of you already know this by heart. You have a filter, you scan this filter over the input, you get an output, right? That's very standard way to do convolution. And our approach uses that with some smart insights. So by kernel here, please understand that this is the weight. It's just another name for it, okay? So we project the kernel on top of this, and you keep moving the kernel, right? And you're gonna get these windows. The windows basically are a projection of the kernel top of the input layers for the different channels. So again, your kernel moved to the side, and you get another window. Okay, so once you have this concept of windows, you can basically do the following. You have VSRs here is notation for vector resistors for the power 10 MMA. Okay, you have the notation here. And basically what you do, you get these projections, these windows, and kind of move them to the vector resistors. Okay, you do this for this window, for the other one. Okay, for the second window. So you spread them across the vector resistors. And then you do the same for the kernel, for the weights. Okay, take the weights, move them. Of course, there is some packing here. I'm not going over details on that, just touch a bit. And you do it again to another kernel. And once you fill in all these vector resistors, you can do the auto product, right? You can start accumulating that in a regular auto product approach. And you can do, for example, this first one, and it's auto product, right? You do this guy with all this, A with 1, 2, and so on, J with 1, 2, and so on. And once you do this, you produce on this accumulator the partial results of the computation, right? Actually, if you look carefully, the inner product and outer product difference is how do you do the associativity of the computations. It's basically the difference, right? So you accumulate this on the top of that, you do the first outer product, and then you go and do the second outer product and accumulate on top of it. The nice feature of that is these are resistors. You are basically accumulating on top of resistors, and you are not moving data to memory, okay? So you take the previous result, and you get the second result, add on top of it. Of course, there are a number of features related to scheduling, precision, about the order that you do that. I'm not going into these details, but you keep doing that and accumulating into registers. That's something that, in general, people have been discussing in the task groups of RISC-V International about should you have accumulators or not. Accumulators add area, right? On the other hand, it gives you a very good boost in terms of computation intensity. So having accumulators in architecture pays off, provided that you want to pay the price for the extra memory for that. Right? I mean, it's a very simple equation, n times n divided by n plus m. You can show straightforward that accumulators are really important to speed up the computational intensity. Okay, so continue doing this, accumulate on top of that, have not moved out of the processor. The accumulators are resistors inside the die, right? And we repeat that for all for all the kernels that you have, all the inputs, and then you are done, okay? All right. I mentioned before that one of the tasks of the computation slice optimization is input packing, right? Packing is really important. I keep repeating this to some folks because sometimes people say, hey, let's do this microarchitecture. Something happened here. I don't know why. It came back. And the people don't think much about the relevance of the compiler who's going to use that, okay? It's really important to have this integration of compiler folks and hardware folks when you design an architecture. Otherwise, you're going to have this very nice hardware architecture that compilers cannot use that. Remember John CUHK in the 80s when he said, well, why I have all such great instructions in this experimental processor at IBM, which move one table from to another place. A single instruction can provide a pointer to a table, give the size of the instruction, single instruction, and provide a pointer to another table, and you move the whole table there. And I write a piece of C code, but the compiler cannot use that, right? Because you can different versions of C code that basically the compiler is not going to be able to map that direct to the instruction. How do you recognize the problem of recognize a fragment of C code that corresponds exactly to a single instruction? We know that this is undecidable, okay? In the 80s, so sometimes people keep designing architectures which are not compiler friendly, and they keep asking, hey, why my compiler is not exploiting that? Remember, 80s, CISC vs. RISC. So it's really important to have these two folks talking together in design architecture. All right, so another thing is this. People say, hey, this is an architecture which provides me a very efficient computation, but keep forgetting that packing might become even around 20% of the execution time. Because packing is touch memory, move the data to the processor, and touch memory again. And you don't want to touch memory, okay? So, but you need to do input packing, okay? So what you do here is you have all your windows, and you algorithmically, symbolically, you move these windows and take, for example, the first element of each window and move it back at here. You can go through the details on the paper. And you then have the second element window and so on, right? If you do that, combine that with I just mentioned, you will have a reasonably efficient execution of that. But there is a very useful observation that came out from this approach. We noticed that if you get the first window packet, and then you move to the second window, if the stride is 1 of the computation, you know that you just need to do a shift on the registers. See, what you could do is take the data from memory, bring to register, memory penalty. Repack it in somewhere in memory miss, cache miss, okay? The other way to do this is do the packing inside of the processor, okay? And we noticed that, by we, you're gonna understand who noticed that. You have the vectors here, and to get the packing for the first window, and the packing for the second window, reusing the data which is already in vector v0, you can do just a shift for stride 1, okay? That's a feature which is shown to be quite relevant performance-wise. So what we did basically is in the Power 10 MMA architecture, you have all these vector registers. And they have something similar to the VLAN in the RISC-V architecture. You can replicate instructions to do a similar work with many vector registers. So basically, they have an instruction in which you can lay out all the data and do a shift, connect vector registers. A full shift with all these 4 vector registers will result in the packing for the next window. And you do that inside the processor. You don't need to take all this data from memory and basically write it back, store it into memory, okay, paying the price of the latency to go into memory. You can do that inside the processor. And this insight was quite interesting. It produced very interesting results. And they basically use a vector-based, we call that vector-based packing approach. We use the vector dialect from MLIR to do that. And it actually produced some interesting performance results. Where's my share? I'm fine, 10, thanks. Okay, let's talk about the results on this. We ran all this tool chain into 8 models. And for x86, it works for x86 as well, and Power 10. And it produced for the convolutions. This is just for the convolutions. It produced reasonably good speedups, okay? If you throw that back into the model, the speedups reduce, but of course, because you're just optimizing the convolutions, right? And we actually were using the ONIX framework, and what's actually not doing a great job with respect to the other operators in the model. Okay, so the reduction here is, of course, you have to improve all the ReLU and so on operators, right? And they need to be very attached in your compiler toolchain. But considering just the convolution, the speed up was quite reasonable, right? Sometimes people get 5 to 10% speed up in compiler technology. They say, hey, that's reasonably great. We compare that with 1 MKL, 1 DNN. SConv is the name of the technique. It's sliced convolution. It's the green bar. And for the different models here, blue bar is 1 MKL, and the orange bar is 1 DNN. And overall, we managed to get very good speed ups with respect to them. Sometimes we lose a bit here, but not much. And we're pretty much happy with the results. All right. So, but how many convolutions do you get this speed up? Actually, if you look at the Power 10 and x86, you have on x-axis here, the convolutions sorted by the speed up. And y-axis, you have the speed up. And you're going to see that approximately 90% of the convolution get very good speed ups, okay, around that. But those which didn't, most of them are point-wise convolutions that you can actually map directly to some regular gem, right? But we didn't try that. I mean, it's quite straightforward to do that. All right, so why does it work? Actually, it's very simple, right? You're saving cache misses, right? Basically, we did a comparison on x-axis here, had for each model, the baseline, the SConv, which is a result technique, and then reducing the cache miss rate for L1, and we are also reduce the cache miss rate for L2. So at the end of the day, is improving locality, okay? The speed up come exactly from improving locality, which is the game for machine learning. It's moving data. Focus on moving data. Computation is a solved problem for AI. That's why I mentioned that's a boring problem, right, compiler-wise. It's complex because the tool chain is complex, because you have to deal with all the idiosyncrasies of MLIR dialects, but overall it's a boring problem. Right, this was published at ACM Taco some time ago. The first author is Victor Ferrari, who's here. And it got contribution from folks from University of Alberta, Professor Nelson, from Jose Moreira, from the IBM research, and João Carvalho is now at AMD. He was doing an internship at Alberta those days. It's my student. And yeah. And interesting enough, this result got the Best National Dissertation Award 2022 with the Brazilian Computing Society. Okay, and that's him. Raise your hand, Victor. That's actual guy. He's receiving his award here. And after that, he was hired by IBM Research, and he is a research scientist at IBM now. Okay, so let's jump to another architecture, right? I mean, I mentioned that depending on the target, this can be very complicated. Doing a generic approach is very complicated. So I will speed up. So we got a variation of this called tensor slice optimization, right? Which most of the difference is the following. We don't have a cache hierarchy. You have like a scratch pad inside the die, and the compiler has full control with the data movement, which is really nice, right? But it's a lot of work on the compiler. It has to manage this data movement, the load stores. So we did that. We used the neuromorphic engine from LG. This was a joint work with the LG labs in San Jose, in the Bay Area. And the architecture is very neat. They have like 4 tiles or more tiles. Each tile has 8 tilets. The tilets have basically a RISC-V processor, a MAC unit, and the buffers, the input buffer, the wait buffer, the output buffer, and as I said, no cache hierarchy. The compiler has to handle the memory loads and stores. So it has to say what I'm going to bring in which timing, okay? Because it does have this nice feature of cache, which at the end of the day costs a lot of die area, right? So they have 32 RISC-V cores, 4 tiles, 8 tilets. The host outside here is an ARM host, but the accelerator is entirely RISC-V based, okay? And it's on chip DRAMs. It's kind of fast. And they do a lot of parallel MAC unit computations. This work was initially done by LG. LG spun off a company called AMI Future. And we continue our interaction with them, did a compiler tool chain design for them, and also for ETRI, an institute in Korea. All right, so we managed to have 2 tool chains for that. One is Keras TensorFlow Classic thing. That's this convolution slice analysis and convolution slice optimization there. And the other one through the MetaGo Glow compiler, starting from Onyx, okay, down to RISC-V. Okay, so it's very simple. Same idea, but compiler has full control. You bring the green block, remember the input stationary, and then you go around these blue blocks here, which correspond to the weight to produce the output. So again, you bring one green block, and then you go around with the blue blocks, which are the weights, doing the convolution, and then you are done. One interesting thing of this work that I would like to call attention is people not paying much attention on burst analysis. What I mean, for those with you which know quite well how memory works, if you touch a data here, you're going to bring it down to the row buffer. And it takes approximately, for example, as far as I remember, this is DDR4, 14 nanoseconds for the CAS latest to bring this data here through the sense amplifiers. To touch the first byte, if you touch the other 127 bytes, it's going to take more additional 14 nanoseconds. So you want to touch a byte and touch the byte next to it, okay? Because you don't want to touch a byte which is outside of the row buffer because the data is already here. This is very common in GPU, but people are not using that actually much to do the tiling, okay? So we use this information to decide what is the best tiling. So in the x-axis here, you have the slicing bytes, W, and y-axis here, you have the time, microseconds. So there is this very interesting cyclic behavior depending how you do the tiling, okay? So you symbolically try to see what is the best tiling I can do, okay, such that I minimize or maximize the usage of the data which is already in the row buffer, okay? So we did that, and we embedded this into the tiling algorithm. So the tiling algorithm knows which memory it's using and is designed the tiling taking this into consideration. What we found is quite interesting. I mean, you can reduce around 23%, sometimes 15% of the execution time just by also looking at burst count in the tiling process, okay? People know that pretty much on GPUs for a long time, but we used that a long time ago, actually. This is work of 5 years ago or something, or 4. So we do the roof line for this architecture. That's the, on the x-axis here, you have the traditional operation intensity. Y-axis, you have the number of Gmax per second. This is the theoretical peak for that architecture. That architecture has a little problem. It's actually, it's not a problem. The way they designed the DMA engine, they should have make it a little bit more efficient. So when you run it through the actual performance that we tested, the roof line is not this. This is the theoretical one. If we take into consideration that actual bandwidth, it's going to be like this. Each little dot here corresponds to one of those models I mentioned. So they are pretty much close to the top of the roof line. Besides the traditional LNet, which is so small that anything you do with it is overhead, right? Of course. This is very common. This is a work which is done by a student of mine, Rafael Souza, with folks from LG in San Jose Labs. Michael Frank, which was a guy who worked senior guy who worked for IBM for a number of years. And I kind of organize everybody. All right, so Rafael Souza is also a research scientist at IBM Research nowadays. And okay, that's my last slide, right? No, there's one more. It's just the, what are we doing right now? We want to design a compilation flow which is kind of generic using the transform dialect. It's a very big challenge. We have a group that Victor is also contributing. And the goal is to make some sort of generic open source compilation flow, okay? It's a challenge because transform dialect is very efficient, very good, but it has lots of hiccups there, right? And I don't go over much of detail what this work we're doing right now, but it's something like this. We go down from linalg and then to vector. Why are we going through vector? Because lots of matrix multiply engines are going down to vector, like AMX from Intel, the RVV is there already. The MMA, we are trying to contribute for that as well. And what we call the RISC-V matrix extension here. A low-level vector extension to address the future matrix extension by RVV. Okay? I have a colleague of mine, Professor Lucas, who is the program co-chair, is going to talk about this architecture that we are designing in partnership with Eldorado. All right, so the idea is to prepare a paper, submission, supercomputing, workshop for LLVM. Let us see if it goes through, right? But there are we heard very good feedback from some actors in the compiler technology area because they are really expecting the transform to be very efficient and a very good tool to design generic compilers for AI, okay? Let us see. Okay. Thank you, folks. That's it. Time?
So we still have time for questions.
You all saw this matrix stuff happening here, a long explanation, but you don't know that Professor Guido was one of the initial leaders for matrix work with RISC-V. He was leading the IME initially, and help shape everything that we know today. So he's continued to be influential in everything we are doing. So all this work is being applied today in different areas, not just in IME, but other, with results, he put all his students to help us make numbers, to make sure things could work properly. So there's a lot of things that's happening that go beyond what he showed here to us. So that's it. Thank this guy, because we're doing a lot of things here because of him.
I have a quick high-level question, Guido. In this very last work that you are showing, you show the slide there with, going to the transform, etc., and getting to various architecture. How much of the details or the specification of the architecture has to move up to the higher levels? Because you mentioned RISC-V, so how much of that is a generic and how much of that is...
Got it. Yeah. All right. So until you get to the microkernel, okay, the microkernel is, you can design a Martian architecture, which is speed of light speed. And you can encapsulate behind the microkernel API, which is compatible with BLAS, okay? And then you have categories of architecture. In architecture, which is memory hierarchy based, you have to move up information like L1, L2, L3 sizes. And ideally, you could also move up information about the memory system, how efficient it is, the cache length, to embed that burst analysis into your approach. That's pretty much it, okay? If it's a scratch-based approach that you don't have this automatic cache hierarchy, compiler will handle that. Again, you're gonna have to move the information of the input, output, and the weight, buffer size to that, and also the cache latencies, okay? So that's pretty much. But it's two classes of architecture. So architecture satisfies, it's basically information related to the memory system, right? The intricacies and the details about the microarchitecture to do the computation, you can hide them behind the BLAS call.
So the microkernel takes care of the computation.
Yes, yes. And you have to raise the level of information for the tiling of the memory hierarchy that you're using. Okay.
Any further questions?
Professor, thank you very much for the explanation. I have just it's really a doubt. If based on your knowledge, if you want to privilege to increase the number or the size of registers and decrease the number or the size of cache, given this operation of convolutions, so what would be your advice on that? For a hardware guy.
I understood. Yeah, thanks for the question. You see, AI is a data movement problem. So having large caches is going to be always beneficial. Right? Having large vectors, of course, is going to be beneficial. The problem is how much is the budget for your tape out? At the end of the day, that's the metric, right? If you are willing to pay more to have a cache hierarchy there, that's great, right? If you are willing to pay more for a larger vector raster file, that's also great. But if you don't have the money for that, maybe you want to outsource that to the compiler to do the data movement. It doesn't use a cache-based hierarchy, right? Because you want to have an embedded device, for example, right? So it's going to depend. And the answer to your question is, how much money do you have to pay for your chip tape out?
Consider another point. So when you implement registers, it's the same process as the rest of the chip, mostly. When you implement the cache, in many cases is the same process, in many cases is a different process. So it's a very added cost on that. Based on this information, so do you keep your statement?
Absolutely. I mean, you see, if you look at a typical design there, if you look at the cache sizes and the core, the cache size is going to dominate, right? So if you have the money to pay for that, why not?
Okay. Thank you for the presentation. Since you dive deep in the cache number sizing and optimization, and later on you move to scratchpads that are probably very custom designed by specific machines, do you have any tips or lesson learned that may help people design newer scratchpad on sizing and dimension and quantity?
Yeah, that's something that we are doing a lot of research on analytically modeling this, okay, with the help with Professor Lucas, Professor Sandro, and Professor Zaias, okay. There are a bunch of work that we're doing, particularly how many accumulators you need, okay. What is the shape of the tile? The shape of the tile sometimes dictate your performance. It's really amazing that, okay. So their grad students are working thoroughly on that, and we hopefully we have a lot of stuff written, but I didn't have put that together in a paper. So we're planning to do that, to give feedback to the architecture designers.
I believe we still have time for one quick question.
Oh, there's over there. Oi, César, tudo bom? It's a hidden question. You guys can see him.
First of all, thank you for the insightful presentation. I have two quick questions. So the first one is, how do you choose the blocking size for the convolution slicing? And the other question depends on the answer to the first. So,
okay. As I mentioned before, we use this binary search algorithm, okay? And so that, I mean, of course, you're going to divide things by 2, and it's kind of far-fetched in terms of precision, away from the best result you would get using ILP, but it's still faster, okay, and produce reasonable results.
Yeah. So what if this block doesn't fit in cache, and if with this arbitrary decided size, how do you ensure good processor utilization?
Actually, it's not arbitrary, because in binary search keep dividing things for 2. Eventually, they're going to get 1 byte block, right? It's going to fit in the cache, right? Or not.
Yeah, okay.
That's an exaggeration, of course.
But how can you ensure good processor utilization?
Well, it's heuristic, right? You can only assure that it's going to be the best solution if you run it exhaustively, or if you do some ILP, long time compilation time approach.
Okay, thank you very much.
Sure.
So let's thank Professor Araujo again.
Thanks.
So please bear with us while we set up for our next session, and we will be back at 9:30.
Now we have Professor Qiang Xu. He's a professor at the Chinese University of Hong Kong. He also serves as the chief scientist of National Technology Innovation Center for EDA in China. His current research includes areas of AI and EDA. He has published over 200 papers with over 10,000 citations, including the most prestigious paper in 10 years, according to ICCAD. Really impressive. Thank you very much.
Thank you for the kind introduction. So, good morning, everyone. I'm Qiang Xu. It's my great pleasure to be here to share my thoughts on this exciting topic, EDA in the era of AI, what large models bring to chip design. So right now we are at the pivotal moment, right? So we have well-established EDA methods, but they are struggling with the constantly increasing design complexity. On the other hand, we have groundbreaking AI techniques that boost productivity dramatically, right? So we want to explore how we can leverage large models for chip designs, right? So let's look at first look at where we stand right now, right? So IC design complexity keeps exploding over the past decades, right? So as an example, you can see that the Apple A11 that has 4 billion transistors right now, like recently for the Apple M3 Max, we have like 92 billion transistors on this chip, right? So you can imagine like we have almost 100 billion transistors working on a, tiny chip that works functionally very well. That's a very complex task. Right? And then of course, the design complexity will drive the skyrocketing design cost, right? And also extended the time to market, right? So these are the problem that we want to address with EDA and AI techniques, right? So traditionally, how do we address the design complexity? So basically, there are mainly 2 strategies. One is we do IP reuse, right? And the other is that we take a systematic divide and conquer. So we break a very complex tasks into like small subtasks and divide and work on them one by one, right? Eventually, we combine them to get the final solution, right? So this is what we have been doing for several decades, right? And then you can see that because of that, we have this waterfall IC design flow with EDA for like several decades, right? So this is a figure I extract from a 1992 paper, and you can see that pretty much we didn't change much for the design, right? So we start with the specification, and we do architecture design, then we do RTL, then we go to logic synthesis, and then physical design, right? And this is like a linear sequential process, right? So that's, by dividing this design stage into these multiple stages, right? So we actually dramatically improve the productivity. But on the other hand, it inevitably leads to the PPA loss, right? So which is because we divide them and then there's an information loss between the stages, right? So we cannot optimize the whole design globally, right? So there's a trade-off between the productivity and the PPAC, right? So this is where we are now, right? So, but what we want to have is something like, we can continuously push the boundary, of the design to the PPAC ceilings. And at the same time, we want that the time to market to be as short as possible, right? So there's a significant gap between where we are now and where we want to have, right? And then with AI, that's, we learn from like massive data, can we close this gap, right? This is the question we want to ask, right? And then there has been a lot of work in the past that AI for EDA, large models for EDA, and then and so on and so forth, right? So we want to explore all these methodologies. So even before the large models like GPT comes out, so we have, there are lots of works for AI for EDA, right? So basically, you can classify it into 2 kinds. So one is basically you do predictive learning. So for example, you have a placement without even do the routing, you want to predict whether where is there is going to be a congestion, right? Using this, let's say CN or transformer, whatever it is, right? So we can do design metric prediction, and then we can revise, optimize the design before we actually go through the lengthy physical design process, right? So that's one method. The other is going to be through, we do reinforcement learning, right? So like Synopsys.ai or Cadence, they all have these kind of tools, right? So basically internally, they still want to predict the current parameters that in their tools, whether they are going to lead to whatever PPAC metrics, right? Then they want to tune it to get a better PPAC, right? So this is what we have for the AI for EDA, right? So I would like to argue that AI for EDA is not good enough, right? The reason is like this. So fundamentally speaking, when we do learning, we actually learn a data distribution, right? And then we can do this, let's say we train our model from the design A and design B, and then we deploy it. Of course, it's going to be working well for the similar designs, right, to the A and B, right? But if we don't see the design C here, then you're actually going to be getting a very bad result, right? So that's basically like so-called out-of-distribution samples. But you can imagine that the designs actually are quite different, right? So if you just learn a few designs and then want to apply to a new design, then usually it doesn't work, right? That's one of the reasons why we publish hundreds of papers from AI for EDA in the past, but almost none of them is applicable in the reality, right? Reinforcement learning works, right, for a particular design because they don't care about any other design. They actually focus on the design they are currently working on, right? So tune the parameters of the tools, right? So that works. But for general, you want to predict the design metrics, it actually doesn't work, right? So this goes to the fundamental challenge in the machine learning, right? So basically, you have the training data. If your test data is within the same distribution of your training data, then it works well, right? But if you get a cartoon dog here, right? For example, you have OOD data, right? So auto distribution, then the model collapses, right? So it doesn't work. So this goes to why large models is dominant today, right? So how large models solve this problem? Because in the past, there are lots of work trying to solve the OOD problem, right? So we have, for example, transfer learning. We have meta learning, all kinds of learning techniques try to learn from a small distribution, but we want to be applied to many other domains, right? But it turns out that the easiest way to do it is simply just increase the compute and data, right? So we basically have a large model that take all the data in, right? So once we get all the data in, we learn a general data representation, then we can actually apply to many tasks with zero shot or even zero shot on fine tune for specific applications, right? So basically, I think the main reason why large model works is simply that you use so many data, there's almost no out of distribution data for you, right? So basically everything fits in, right? So that works, right? So this is the reason that we have the AI development. We have several stages, right? Starting from several decades ago, we have machine learning techniques and go to deep learning. And then today, we got all sorts of large foundation models, right? So they can work on, almost any kinds of data, right? So now, based on the large language model, right? So we have right now so-called multimodal large language models. So basically, they work for many different kinds of data, right? So besides text, including image, voice, some 3D signals, lots of them, right? So the question we want to ask is today's large model, we can work on all these things, right? So how about we do circuit design optimization with the large models, right? Can we use large models directly, and then they can help us to design and optimize our chip, right? So before we actually go into the detail, I want to divide that when we want to solve an interesting problem, there are two kinds of efforts, right? So one is the human effort to generate the solution. The other dimension is actually we want to execute this solution, right? So that's going to be the computational effort, right? So you can see like lots of different tasks, how they fit in this figure. So you can see like, for conversation, it's like you don't require much human effort, also don't require much computation effort. Artistic creation, like you draw a figure, draw a picture, and then that takes a lot of human effort, right? And then we have also task planning, hardware, software coding. So all these things, right? So they actually take lots of human efforts, right? So we want to generate the solution. These are all going to be disrupted by the generative AI, the large models, right? So they are here to replace us, right? They can do all these things, right? So on the other hand, there are lots of other tasks, right? So they probably doesn't need quite much like the effort on the, the solution finding, right? So basically just execute this solution, right? The execution this procedure, right? So like scientific computing, design verification, design optimization, all these tasks, right? So they actually, the algorithm is there. So basically, you just need to take lots of time to execute the task. Like for example, let's say logic optimization, right? So you just need to take this entire circuit and start with a substructure one by one, right? Try to replace it with a better substructure, right? So that just takes a lot of time. So these are actually, right now we are still relying on conventional tools, right? So the question is like in the EDA domain, right? So we are focusing more on the design verification and design optimization side, right? So whether the large models can be applicable to this domain, right? So far we didn't see much success, right? And then we need to analyze why, right? So for example, I show a typical verification and optimization problem, right? So the optimization is like you change the structure to a reduced structure with less delay and the area. Equivalence checking is like you have, two circuits which are complex, but they are essentially identical, right? So LLMs, at least for now, right? So you cannot predict the future. At least for now, it's not good enough to solve these problems, right? Computational heavy problems, right? And then, so we want to understand why, right? So why, like, they can actually come up with like new algorithms. You pretty much you see like a news of the large language model, the capability getting a new high like almost every day, right? So why it cannot solve our problems, right? I think there are two fundamental reasons, right? So one reason is learning. First of all, learning is about, first I need to represent the data, right? I want to learn, I need to represent it in the vector space, and then I can do all sorts of computations on top of it, right? So compared to the text or image, what's unique about circuit is that for the text and the image, these type of data, right? So all the information you want to learn actually exists in the raw data. Basically, like all the information is out there. Circuit essentially conducts computation, right? So you give your circuit, if you don't run simulation, you don't know whether this given the impulse, what the output is, right? The data, putting it there, it doesn't contain the information, right? So you have to do the simulation or other things yourself, right? So that's a key difference, right? So you can now just throw in all these circuits and use the same like large model, let's next token prediction to train the model and to learn the circuit, because simply doesn't contain such information. Right? So you have to have some way to put this information back in, right? So that's one reason why it can't. The other reason is that most EDA problems are NP hard, right? So of course we are going to use all sorts of heuristics to solve it. But the heuristics can be having like the heuristics, basically like for these complex problems, one property is that solving it, the difficulty of solving it is directly proportional to the size of the problem, right? So it can be n squared, it can be n log n. But LLMs are very different, right? LLMs basically is you have the network trained already there. So basically every time you generate the token, the number of computes is fixed, right? So right now we are in the LLM domain, so we are doing lots of reasonings, right? So basically reasoning is that you generate lots of intermediate tokens, right? Eventually, before giving the eventual answer. But still, it's a linear scale, right? So you can generate like, let's say, 100,000 tokens for this particular problem. But the heuristic we want to solve this problem requires, let's say, n squared. Then you are never going to match this compute, right? So basically it means that for certain complex problems, you want to rely on LLMs to solve it. It's simply impossible. Right? So you need. So basically it means, with LLMs, right? So we can use LLM agent. We can generate some Verilog code. We can generate some scripts, right? So we can reason certain issues during the design process, right? So of course, they are going to give us some benefits, right? But that's not going to be much because it doesn't solve the core problem of the core EDA complexity problem, right? So that's why I should draw this. So in the short run, we will see lots of LLM agents, and then in the chip design domain, right? So they are going to work, but not going to. But we should not expect too much from it, right? So what we need is actually we need some dedicated large models that can truly understand circuits, right? And then that's going to help us to push this PPAC boundaries to the ceiling. Right? So that's what we need, right? All right, so that's why we start this so-called large circuit model project. Right? So the key observation or the fundamental rationale behind is that we see this IC design process as a multi-modal transformation procedure. Right? So starting from the spec is going to be in a text or figure, right? And then you have a code in the RTL. Then you have like a logic net list. That's going to be circuit net list, circuit graph, right? Then go to physical design. It's going to be with geometries information, right? So you can view it as I'm trying to transfer from one modality to another modality, right? So the design process. And then if you think about this, from this perspective, it's going to be, in the higher level, we have like a more semantic information. In the lower level, we have like more structured information, right? But eventually, so what they are doing is actually you have the same functionality, right? You want to achieve the functionality and your PPAC goal specified in the specification, right? So that's the constraint you have, and then you have a transformation process from the initial spec until the last physical layout stage, right? So from this perspective, we can actually try to generate a large circuit model that learn from every stage, right? And then do the alignment to have a representation that capture all this information. So this is if you think kind of similar like the current AI frontline is like video generation, right? Image generation has been very successful, right? So basically you can see like why we can do image video generation is basically we do a text and image video alignment, right? So we know semantically they are the same thing, right? And then here, basically we borrow the idea that all these design stages, they actually implement the same functionality, right? So that's a strong constraint that if we can learn the representations and align based on this assumption, we can get a representation that capture all this information, right? So that's kind of solve the problem that earlier we talked about. We do the waterfall design methodology that we lose certain information during each design stage, right? So now we can see the global picture, right? We can do a prediction from the very early stage to the later stage, right? So the key idea is that at every stage, we do representation learning, and then we do alignment to get the aligned representation, and then we apply it to all sorts of EDA problems, right? We can also generate possible new EDA tools. So then the number one question I always get is going to be the data. How you want to learn this, you have to have the sufficient data, right? And then how to solve this. Also, in the hardware design community, it's not as open as the software community, right? So we have like high performance Qiang Xu projects. It's a very good candidate, right? But very few of them have such a high quality data, right? So if you think about it, is the main data problem we have is the RTL, right? Because from the RTL to netlist to netlist to physical design, that's a one-to-many mapping, right? We can actually, from one RTL, we can generate many netlists with different synthesis script, right? So we basically lack the RTL, right? And then secondly, it's like, if you think about it, the hardware design, there's a unique benefits for the learning is that we are not going to implement everything into the hardware, right? So basically, like the number of the possible type of chips are limited, right? So you have all kinds of processors, all kinds of like communication chips, and then so on and so forth, right? It's actually a limited set, right? If you go one step further, let's say the digital chip, right? They are all composed of data path and control path, right? So the data path, control path, data path basically is, the all sorts of multiplier, systolic array, all these things, right? And then control path is actually all kinds of decoder, and then mux, whatever it is, right? So basically, which means the hardware, the chip design has very high data bias compared to text or software code or other things, right? So this is what you have, right? So if your data have very high bias, basically means it's very easy to learn because you are learning a distribution that is has a very obvious shape. Let's say put it this way, right? So we basically collect lots of RTL data, and then we generate the netlist. We also do the physical design. So we have make all them open source already, and then we train our model on top of it. So that's the data set part. So then, so in the next few slides, I'll go through like a few advancements of our large circuit model. But I'm not going to go to the very technical details, right? Because it's simply not sufficient time, right? But the point is like, as earlier mentioned, we try to learn from every stage, the representation, right? So this is, we start with learning the netlist, right? Because that's bridge the front-end design, the post-end design, right? So we actually do a serious work called Deep Gate to learn the circuit netlist. So what we want to prove here is that you want to have a large model, then this large model needs to be also abide this scaling law, meaning that if I give you more data, the model keeps getting better, right? So if you cannot have achieve that, then basically like you still have a small model, right? So that's going to saturate, right? So we basically try different architecture. Eventually we choose like graph neural networks. We use graph neural networks as a tokenizer to tokenize the circuit, and then we use the transformer to put them together, right? So that's a GN plus transformer. Eventually we prove that it's going to be applied by the scaling law. So basically like you give more data, then the loss keeps going down, right? So it gets better and better, right? And then another thing is that we separate the circuit embedding into two types. So one is we have the function embedding. The other is the structure embedding. So why is that? Is that the, two circuits can be very different in structure, but they have the same functionality, right? So you want to extract this, you want to make sure that they are separate, right? And the structure embedding is also very important because eventually the PPA is mostly dominated by the structure property, right, inside the function, because it doesn't care what function is, like critical path is there, then, you know, that's the delay, right? So then we apply it to several EDA applications. So if we learn the logic, so we can, one thing we can do is to apply it to set solving, which is a core engine for logical synthesis and formal verification, right? So one is so basically for the functional embedding, if we take advantage of, we do several works, right? So we take advantage of functional embedding, we try to find those circuit elements that are very related or similar in function. We basically like put them in opposite value in front, because the set solving is a problem. It's like you want to find the conflict in the circuit as soon as possible, right? So we try to create the conflicts as early as possible, right? So that's brings lots of benefits. And the other thing is we try to remap the circuit into, using the structure embedding we have, we map it into a circuit that is friendly to set solving. Right? So usually you map a circuit for the timing or performance, timing or area or these things, right? So we actually can, when you do formal verification, like you don't care about the area and other things, right? But you can actually remap it to a circuit that is easier for the set solvers, right? So that solves the, that can reduce the solving time by an order of magnitude. And at the RTL level, right? So we do understanding, generation, and the PPA prediction, right? So this is, so because we want to eventually try to align all these representations, right? So we cannot just take the existing decoder-only language models on RTL. Right? So we actually have encoder, decoder, architecture for our model, right? And then, as you can see, that the result in terms of understanding, generation, and PPA are all SOTA at this moment. We are still working on the third generation of deep RTL. Is that right now we focus more on the code, right? But we are going to have a multi-view representation learning. So not only the code, but also the control data flow graph of the code. So basically they show the different properties of this code. So we try to align them together to get a better result. And then, so recently we also do the, earlier we talked about deep gate, we do the AND inverter, this NAND list, right? So we do alignment between basically like the pre-mapping and post-mapping, right? So we do alignment, and then, so the alignment is also very simple. So basically you have a circuit NAND list that is pre-mapped and the other one is mapped, technically mapped, right? So you can mask one part and use the other part to restore it. So if you can do this successfully, meaning like your representation understands the mapping relationship between this, the pre-mapping ARG NAND list and the post-mapping list, right? So, and then you can see like this cross-modality alignment indeed improves the both the representation capability, and also we apply it to an EDA problem called ECO, the engineering changing order, so that we can actually reduce the ECO cost by, on this benchmark by like 15%. And then we are also doing the, this is a joint work with Professor Eberlin from Peking University. We try to learn the layout representation. So that's, so basically we have the placement data, and then we have the circuit graph. We have also the geometry information. We want to be able to represent it to show the, this is here. So this is our result after. It's very hard to control. So basically the deep layout is actually, you can see that it's very similar to the ground truth value, right? So we apply it to, like congestion prediction and all these tasks. They actually also show the SOTA performance. And then we also do the arithmetic circuit optimization. So basically, like if we consider arithmetic circuits, you have, let's say the prefix, the tree, right? So you have a different kind of configurations. They are discrete values, right? So we actually map them into the continuous space in diffusion, right? So then we can, after learning the latent diffusion, we can actually sample a new design that is possibly better in terms of PPAC than whatever you have seen before, right? So that's also shows some advantage. So in the long run, right? So in the long run, what we want to have is to, in the middle is actually the large circuit model we talk about. We do the alignment between all these, among all these design stages, and then we can actually serve both the verification and optimization problems, right? So for example, for the form verification problem, because our cross-modality representative learning knows the information between steps, right? So we can actually, so for example, this equivalent checking in the circuit net list is very hard, right? But we can actually possibly reverse engineer this circuit net list into the RTL space, right? So what is actually written in terms of RTL, right? And then you can check on the higher level space, right? So that's going to be making it much easier, right? And on the other hand, for the cross-model optimization, what we want to have is, right now we are working on the RTL rewriting. So basically, you can, given a code, right? So you can rewrite it with the same functionalities, but hopefully it's going to generate a better PPAC after going through all these stages. But whether or not it can generate is still based on the, the model you have. You should have a more precise prediction, right? So that's still being supported by the large circuit model. And then, so we want to be able to integrate this AI native large circuit models into the entire chip design flow. So finally, what we see is, we still have like a language model as the interface, right? Because when you interact with the human design engineer, so it's still language model, right? And then you can still use language model to generate code and generate script, all these things, right? But you need the support from a dedicated large circuit model to understand the circuit, especially the PPAC, right? So then eventually we want to be able to push this design boundary to the PPA ceiling with a shorter time to market. So, all right, so that's pretty much what I want to say. Thank you.
Thank you very much. Do we have questions? Yeah.
Thanks, Professor Xu. Very thorough, interesting, insightful talk. Okay, it's a very challenging problem, and it's a very good way to address it. I have two questions. One is in slide 13. If you could go back there.
Go back to which slide?
13, 1-3.
13, right?
Yes.
Yeah.
Next one, please.
Yeah.
Yeah,
Yes.
that's the one. Oh, yeah, okay. No worries.
Yeah. Right. Yeah.
I'm thinking that you are there on the left side. You have probably a binary decision diagram, right, for logic synthesis.
Yeah. That's a
Okay.
logical optimization. Yeah.
And basically, it has canonical form. At the end of the day, you can bring all the circuits on canonical BDD form, and then you can have a very classical traverse of it and code it as a prompt for training. Right?
Sure.
I would like to make an analogy with the physics-informed AI. You have like a regular solver talking with an AI model on the side,
Right.
and feeding the information around,
Sure.
right?
Yeah.
Do you believe it would be possible, because you said that it's a challenge problem, right?
Sure.
Would it be possible to do the regular BDD encoding and go to the canonical form, and then have that interact with a MIS-SYS-based logical optimization model, the classical one, to get some corner that the regular MIS-SYS logical optimization process can't get out of in terms of better circuit
Right,
results.
right, right.
Is that possible? Do you
Yeah,
think
excellent
so?
question. That's indeed possible. We're actually also exploring that. But what I want to emphasize here is that the LMs itself won't be able to solve this optimization
You have to
problem.
complement with
Yeah,
that of the solver.
if you have a
Okay.
solver together, then you get some feedback, then you can actually turn into the loop, right?
Okay.
And that's
Correct.
that's going to be a very good direction.
Okay. So and also the different levels of the EDA toolchain, you could do that, right?
Sure.
The combination between. Okay.
Sure,
that's
absolutely.
one
Yeah,
question. Yeah.
absolutely.
The other ones is slide 22.
22, right?
Yes.
There's a delay.
Yeah. Yeah. Yes, that's the one.
Yeah.
Some time ago, maybe 10 years ago or 15, Charles Malik from Princeton, and they have this shaft algorithm to do very efficient SAT SAT
Right.
solvers, right?
Right.
Have you compared with those approach? I keep wondering if throwing LLM into the problem can get you better results than the shaft or algorithm.
Actually, the SAT solving has the fundamentals of based on CDCL solver, right? So that doesn't change much. But there are lots of heuristics built in the SAT solving. They actually constantly you get 10%, 20% savings every year, right? But it doesn't change. The main theme is still the CDCL solving, right? So what we want to say here is actually the second work is actually we didn't change the solver, right? We changed the problem. We try to give the SAT solver a easier to solve problem.
Okay.
And then we need to, from that perspective, we need to understand what structure that the SAT solver like. Right? So that's why we do the learning, and then they actually.
So
help
probably
on
you're
that.
used as a baseline shaft, right? Because it's a major breakthrough
So
those
we
days.
didn't change the
and
solver.
you are saying you are getting like 40% around better.
That's the right
top of
hand
it?
side is like depending on the circuit itself, right? Of
Okay,
course, like,
sure. Yeah,
the
of
best
course,
case, like you can get like 99, like you can get like order of attitude improvement, right? But sometimes you get like similar, right? And the left hand side is a different strategy. The left hand side we actually change the heuristic in the solver by observing certain properties.
Yeah,
And
okay.
we change we actually generate more conflicts. So that one save roughly like half of the time.
Okay, that's pretty good. Yeah. Okay. All right. Thanks a lot. Appreciate it.
Thank you.
I just want to continue this question. One curiosity that I had is, you are saying that you are selecting circuits to be easy to solve by the SAT solver, and then you are using those to train the LLMs. Aren't you introducing a bias in your training in that case?
I'm not training LLMs, right? So first of all, we are not doing LLMs. What we do is actually, so basically we have a set of the structure transformation, right? So basically, if you think about like a logic optimization, you have a few commands, right? So one, this structure change to another structure, and then we basically try to understand the structure embedding, and then we understand like this particular type of structure is actually the SAT solver likes, right? So it's easier for them to branch or to find a solution conflict, all these things, right? So we basically use that as a guidance to do the mapping, right? So that's going to probably you get a larger circuit at the end, but it's easier to solve. But this is because this is a verification problem. We don't care about you're not implementing, right? So that's okay.
Brilliant. Congratulations.
Thank you very much.
Can I see the slide where you show the complexity of chips?
Complexity of chips.
Yeah, when you show the
You mean the first slide?
one of the first.
The first slide, right?
Yeah.
I think. Yeah. This one.
Yes,
Right.
here.
Right.
We can see that both in area and cost, the complexity is exponential.
Right.
But we're talking about 2D chips.
Right.
I have two questions. This one, I want to instigate you to ask about your vision about the possibility of we folding these chips in 3D.
Right.
What's your ideas about that?
Sure. I'm not an expert in that, but that's a very hot topic in the the chiplet and then 3D chips. There's lots of work on that, right? That requires lots of information from the foundry, right? And then I used to work on 3D chips like 10, 15 years ago, but I didn't do it much because you have to collaborate with the foundry closely to get the data, right? And then the problem there, I think, is more on the how do you simulate the heat, the temperature, the mechanics, right? Mechanical stress, all these things, right? But in terms of design methodology, I don't think that has like a very different from the 2D, right? So you can always have. So I think current generation of the 3D software, they are actually, revised on top of the 2D, right? Plus these, 3D simulations, right? So, but I'm not an expert, right? So, yeah, that's what I can say.
And can you show the waterfall process, the slide of the waterfall?
For waterfall, right? Okay.
Yeah.
Yeah. Yes. Yeah.
So I think IC design is one of the most complex brain-oriented activities performed by humans today.
Right.
It's very hard to find. And I understand the current limitations of LLMs.
Right.
But regarding the time to the market, the approach of my group, instead of having a global approach, we are trying to address steps of the waterfall.
Sure.
And we do believe that this approach could be, it's a bottom-up approach.
Right.
And I think that could be a strategy. I'm teaching IC design for students, and I'm introducing some AI concepts in the design methodology.
Sure.
Maybe instead of, I want to have your comments about that, but instead of having a super OEM that can do my chip, do the chip, being pragmatically, what do you think about we introducing, instead of large language models, using small language models for specific critical steps on the waterfall?
Sure. I think first of all, like one thing is that I keep emphasizing that LMs are not enough, right, for IC designs, right? Because if you think about it, like you have a circuit, you give to LM, like it doesn't know which one is going to be the critical path, right? Because it doesn't have the concept of the path. You have to analyze the graph structure to get the path, right? So basically, like if you use LMs alone, it won't be able to give you, the correct answer, right? In terms of a PPAC optimization. That's one of the reasons, like, if you see, like, for the code generation, the software code generation is actually, right now, Cursor or Copilot is actually, the industry is actually adopting them, right? But for the RTL, I think people are still working on them, but nobody actually use it in the reality because it doesn't understand PPAC, right? So we want to be getting the best, after the best design afterwards, right? So that's so LMs cannot do that, right? But what I'm trying to say is like internally, as you said, in between different stages, you don't have to have all the holistic, everything to learn together, and then you can actually start to use it. You can learn in between like two neighboring stages, then you can still do a lot of work, right? For example, if you learn RTL and netlist, if they are aligned together, you can see like if I write RTL in this way, most likely it's generated this kind of structure, then that's actually is helpful for you to do the RTL optimization, right? Similarly, like for the mapping and the placement, so every neighboring stage, if you can learn together, you can somehow get some benefits. That's what I think. Sure, of course. Similarly, as I said, there's a couple of different things you can do with verification, right? So one is that you generate test stimuli, right? Or you generate UVM. So that's basically you generate the code, right? That I think the LM can do it already, right? But if you want to have a high coverage of your design, so that's a different story. You have to know why this particular stimuli doesn't hit this branch, for example, right? So from that perspective, you have to understand the computation. So that LM is not good enough. So you still need a model to learn your circuit and then to generate stumbling that's going to give you better coverage, right? And then in terms of formal verification is a different story. Like set solving is a core engine of formal verification, right? So similarly, like you probably can use LM to improve the heuristics you do formal, but eventually like AI is not guaranteed, right? And formal, you want to have 100% correctness guarantee, right? So you cannot use MF end-to-end at least, right? So there are, I think for both, the simulation-based verification or formal verification, there are lots of work. There are lots of problems to be solved, right, using AI. Thank you.
Okay, thank you. Very nice talk. Can you comment how the commercial tools like Synopsys, Cadence are adopting machine learning models or large language models in their tools today?
Well, it's very expensive, right? We don't have access. but I know a little bit is that at least for Synopsys.ai, right? So our Cadence have similar solutions. They are based on reinforcement learning. So the main objective is that in their tools, there are lots of parameters, right? If you tune the parameters, they're going to generate a very different result, right? So what they want to do is that they generate a number of seed solutions. They try to see whether, particular parameter combinations cause like a certain result, PPAC, right? And then they will tune it accordingly to generate a design with a better PPAC. That's the main thing, what they do, right? And then they actually focus on a particular design only. And then I also know that they are kind of working on RT, like code generation, all these things, but I think it's not ready to be used in practice. Right? But other than that, that's a very expensive tool. And also, we are banned, right?
It's not yet in the default tools.
Right. Synopsys.ai is very expensive. They charge you based on the number of seeds, right? So you can actually search for the RL in the beginning. That's yeah. But I think the fundamental principle is based on the parameter tuning.
Thank you for the presentation. I wonder if any of these ideas or tools you have looked at the possibility of using for analog and mixed signal design.
Right. Okay. Excellent question. I think I myself is I don't know anything about analog RF, right? So that's kind of an art, right? But I think the methodology wise, it can be applicable. I think people also there are other people take this idea to do that, right? Because from one perspective, I might be wrong, right? But if you look at what AI did in the past, right? So is that whatever we think that's art, it's actually easier for AI, right? So the image creation, music, all these things, right? In the past, we think this is like what only human can do that, right? But turns out that AI is easier to understand that, right? So for analog RF, I think the one thing is particularly helpful for AI is that the design space, you have lots of parameters, right? But the possible type of circuits and all these things are not that large, right? So if you can, feed the AI lots of data, I think they are going to learn pretty much like what human can do. And as far as I know, there are lots of work. There are lots of groups actually trying to do automated analog RF circuit generation, right? So, I'm not an expert there.
So in your practices, when you have a large language model, is it like a one foundation model that handles all the tasks, or do you have any specific large language model tuned to each of the subtasks that handles?
I think that means the takeaway message is not that clear, right? So what we are doing is this one, right? So basically, we want to, in the future, my vision is actually you have large language models as the interface with the human designer. You still need that, right? But at the the large language model doesn't understand the circuit behavior. So you need the large circuit model to actually understand the circuit, and then they work together to give you a better PPAC at the end.
So large circuit model is trained based on the actual electronic data, EDA data.
Right.
Which is not based on the large language model,
Right.
the human knowledge.
Right.
Then do you think the LCM will eventually replace human designers to create the design from specifications?
I think
In the future, I guess.
In the future, my guess is that right now it's like we actually have AI aided human design,
Right.
but in the future it's going to be human aided AI design in the future.
Okay, still the human should be in the loop, you mean?
I think the less and less, right? But in the beginning, you define the architecture and all these things probably need human intervention. But in the afterwards, right, probably less and less. Right? So basically,
Just
like you need.
The last question is the LCM. What's the size of the LCM in compared to large language model in general?
It's much smaller, right? Because the reason is very simple. The circuit is a very biased data. It's easier to learn. Right? From that perspective, you need a smaller model to learn it. Language model is the biggest. If you compare to vision model is much smaller than the language, right? Because language, if you think about it, it doesn't have much bias, right? So that's the language contains lots of information. Right? So I think in all sorts of modalities, language model is the largest, right? And then even if you want to learn, let's say software code, a 7B model could be, if you only focus on code, it's good enough because that's actually also a biased distribution. And hardware is even smaller. So for what we have right now is like hundreds of millions of parameters, not even in the billion level.
But given the search space is large, do you think the LCM size is the limiting factor for your solution?
As I said, like I don't think the model size is a big factor here, because the bias, the data distribution.
I would like to have an idea about the data sets that you are using. What's the size of it, and what's to talk a little bit more of where are the sources that you are using, if you have some partnership with companies that are doing professional designs, and how can you get this data for training?
Right now, the data is like, what we have data is all open source, right? Because companies, it's very, that's top secrets for them, right? But what we want to do is, we do it several ways. One is we do augmentation, right? So we have a RTL. We can rewrite the RTL with the same functionality, but they are going to have different, PPAC matters, right? So we can automatically generate lots of, from an initial RTL, we can generate lots of other RTLs, right? And also, what else? Basically, you do certain optimization in the RTL. So basically, like you do again divide and conquer, try to get a large code base.
But today, how many do you have around? How many?
We actually have a pretty. So basically, like in terms of lines of code, we have like 100 million, a lot, right? And then that list is even larger, right? So as far as we are concerned, then the learning itself is you can see the benefits, right, already. Right?
Great. Do we have more questions? No. Okay. So thank you very much. It was an incredible presentation. Yeah. Okay. Now we will have a break. Okay. Thank you.